Welcome students to this next session on industrial metallurgy. This is session number 44, and in this session we will continue our discussion on the time temperature transformation diagram, that is the triple T diagram. So again I'll show you the neat and labeled triple T diagram for a eutectoid steel, uh, and then I'll briefly discuss with you that what are the different transformation products of austenite which actually are shown on the triple T diagram. And finally we'll see that how was the triple T diagram used initially when it had been constructed. So again you can see that this is the triple T diagram for a eutectoid steel. This is the upper critical temperature for the eutectoid steel. Mind it, the upper and the lower critical temperatures are the same for a eutectoid steel. So, as I said in the last session, above this A1 temperature, the microstructure of the eutectoid steel is 100% austenite, and all this austenite is completely chemically homogeneous, which has no tendency to transform into any other phase. But as you bring austenite to a temperature which is lower than the lower critical temperature of the steel, then this austenite becomes unstable. And if you can spend this much of time at any given transformation temperature, then transformation of austenite begins. So this is the start of transformation curve, this is the end of transformation curve, and this one is the 50% transformation curve. Now let me discuss with you that what is there on the see, on the left side we have this temperature, on the x-axis we on the y-axis we have the temperature, in fact the transformation temperature at which austenite is transforming. On this x-axis we have the transformation time, the time spent at a given transformation temperature, and here we are seeing the transformation products of austenite phase. Now on this y-axis, the right side of the y-axis is actually showing you variation in the hardness of the phases that have been obtained. So here if austenite transforms into a particular phase, that phase would have roughly of a hardness of Rockwell hardness C scale 10. Here it would have increased to 40, and here it would have increased to 60, and over here it would be even more than that. Okay, now but let's first discuss about the various transformation products of austenite. See, the triple T diagram is showing that if austenite transforms at any temperature between 727 degrees centigrade to 550 degrees centigrade, then it transforms into a product phase called perlite, right? But then these perlites have been marked differently. Here in a high transformation temperature region we have something called coarse perlite, then below it we have medium perlite, then at an intermediate temperature we have fine perlite, and at the lower band of this transformation range where actually perlite gets formed, we have extremely fine perlite. See, this perlite, students minded that when you initially had the steel at the room temperature, you heated that steel to some high temperature so that you could have 100% austenitic structure in it. Then you held the steel at that temperature so that the austenite which has got formed becomes completely chemically homogeneous, and then you start cooling the steel. The point that I'm trying to make is that whatsoever grain size the steel was to have has already been fixed through the heating and the holding step. In the triple T diagram, when you just talk about the decomposition of austenite, you just talk about the cooling of the steel. So the heating and the holding steps are already locked. So that means that the grain size which the steel would be showing to you, right, is already fixed. Right, so when I say over here coarse perlite or medium perlite or fine perlite, it has absolutely nothing to do with the grain size. The grain size is already fixed, and that depends upon whether did you heat to this temperature. You might have a fine grained austenitic structure. If you would have heated to a still higher temperature, you would have got a relatively coarse grained structure. Now, when we are talking about triple T diagram, we already have a steel of a given grain size. So here, coarse perlite or medium perlite is having no reflection onto the grain size, right? Here the coarse and fine and medium and extremely fine, these have relation to the type of lamellar spacing that is there. So here when I say that coarse perlite gets formed, coarse perlite gets formed means we have wide, coarse, few lamellas. But when I say extremely fine, the amount of perlite, the amount of ferrite and cementite and perlite would be the same, but the lamellas would be very, very fine. So a large number of lamellas would be seen. Okay, fine. So what I'm trying to tell you is that if the conditions are such that the austenite present in the steel gets an opportunity to transform, to decompose anything between this range 727 to 550, then austenite transforms into the product phase perlite. Mind it, when perlite transformation takes place, austenite transforms to, when austenite transforms to perlite, it transforms in a high temperature range. Diffusion of both carbon and gamma iron of, see what is austenite? Austenite is a solid solution, interstitial solid solution of carbon in gamma iron. Now when austenite transforms at a high temperature, it transforms due to diffusion, number one. If it transforms in this range, high temperature range 727 to 550, the carbon present in austenite and also the gamma iron present in austenite both undergo extensive amount of diffusion and transform themselves to an aggregate of ferrite and cementite, which you call as perlite, right? Then the point, see, in other words, you can also say, see students, here the incubation period is this much. Here the incubation period is decreasing. Here the information period is again decreasing. Here the incubation period is minimum. You can also say that when austenite transforms in a transformation temperature range where any drop in temperature leads to a decrease in the incubation period, in that transformation temperature range, austenite transforms to a product phase called perlite. Okay. Then if austenite is left, or if whole of austenite is still left, unstable austenite is there, and it gets an opportunity to transform somewhere in this range 550 to 220, then austenite transforms into a product phase called bainite. Students, bainite, like perlite, is a mixture of ferrite and cementite only, but it has got some essential points of difference. It always has a non-lamellar structure, and it has got slightly better mechanical properties than the perlite phase mixture. I'll talk about it more when I come to the next part of the session. Okay, so if austenite transforms in a range, but mind it, when austenite transforms from 550 to 220, which is an intermediate transformation temperature range, not as high as is for perlitic transformation, not as low as would be for martensitic transformation. So when austenite transforms in this intermediate range of temperatures 550 to 220, austenite transforms to bainite. Again, this transformation of austenite to bainite is a diffusion based transformation, and when austenite transforms to bainite, diffusion of carbon atoms of austenite take place extensively, that of gamma irons only take place to a small extent. Finally, students, if there is some austenite still left, or whole of the austenite is still left and hasn't transformed yet, and that unstable austenite is with you, and it gets an opportunity to transform somewhere between 220, which is referred to as the MS temperature, to another temperature which is called MF. If austenite transforms in this range, then it transforms to a new product, very hard phase, called martensite. Mind it, martensite transformation happens at a very low temperature. It happens without diffusion. If you will do very, very quick cooling, then only diffusion process will not get to know that I have to occur. It would not get the time to occur. And then austenite has to transform, because at such a low temperature, gamma iron cannot exist, because austenite is carbon in gamma iron. So gamma iron will change to alpha iron, but the same amount of carbon which was present at a high temperature in gamma iron would now be present, the same amount of carbon. Why same amount? Because diffusion has not got an opportunity to occur. And minded, gamma iron has got about 100 times more solubility for carbon as compared to alpha iron. So you had taken austenite, there was some good amount of carbon present in that austenite. For example, we are talking about this 0.77% carbon steel. Gamma iron's maximum solid solubility for carbon is 2.11. It can easily take this amount, 0.77% of carbon in it. But think about alpha iron, maximum solid solubility is 0.02. That also at 727 at room temperature or at 200 degrees centigrade, solubility is about 0.000 something. But because gamma iron was so rapidly cooled, steel was so rapidly cooled, this austenite could not transform to pearlite, this austenite could not transform to bainite, and now it is transforming to martensite, because gamma iron has changed to alpha iron, and this alpha iron is accommodating the same amount of carbon as was present in austenite. In gamma iron, a super saturated solid solution of carbon in gamma iron gets formed. Students, that is called martensite. Very distorted crystal structure, which is called BCT, body centered tetragonal, and exceptionally high hardness because of this distorted crystal structure. The phase is called martensite. So you have to say that, sir, between MS to MF, very low temperature, 220 to room temperature or even sub-zero, if austenite transforms to martensite. And students, mind it, austenite always transforms with a decrease in temperature. When MS temperature is reached, some amount of austenite will transform to martensite. The remaining austenite would say, please drop my temperature, then only I can further transform to martensite. And when would the remaining all austenite transform to all martensite? When you have reached this temperature MF, and this generally is sub-zero. This generally is -10 or -50 or minus. So that means when you are at the room temperature, the entire remaining austenite will not have transformed to martensite. So this austenite, this unstable austenite, which is present even below the MS temperature, has got a very different substructure. The number of dislocations in it, the number of stacking faults in it, the number of other defects in it are far more as compared to austenite when austenite was present at high temperatures. So if austenite has remained untransformed and it is present below MS temperature, it is given a special name of retained austenite. It's only after MF temperature that you get, and retained austenite creates problem because you generally form martensite in the steel when you need exceptional hardness, but presence of this retained austenite along with martensite beats the very purpose. So you have to get rid of it. Getting rid of it is either give a sub-zero treatment to the steel, the MF, reach the MF, or the practical method is to give tempering to the steel. This tempering treatment converts this retained austenite to some other stable phase, right? So this was all about the triple T diagram. Then let us see that what are the various transformation products of austenite. As I said, I'll just repeat along with these schematics that I have made for you. Students, this has been a huge task to create these microstructures for you. We have not taken them from any book. We have actually created them for you. So please, yeah, if we have done some homework for you, little bit of hard work for you, please be involved and listen to the lectures and enjoy them. And if there are any queries, please ask us. So this is the Perlitech structure, always lamellar structure until unless you do something special with it. Always lamellar structure. We have a lamella of ferrite, we have an alternate lamella of cementite, then ferrite, then alternate lamella of cementite. When does it happen? At high temperature, at high transformation temperatures, when austenite transforms due to diffusion, and carbon and iron atoms of austenite both take part in the diffusion, then austenite transforms to what is called pearlite. Bainite. Students, look at this diagram. If you are able to transform austenite in the range 500 to 550 to 400. You get bainite which is called upper bainite or feathery bainite. And if bainite is formed in the range 400 to 220 ms, then it is called lower bainite or acicular bainite. The difference between upper bainite is that it's an aggregate of ferrite and cementite, but lamellar structure is not there in upper bainite. This I have not drawn it because this is just a schematic, but actually under the microscope this appears as the lath of the tree, the strips that you can peel out from the trunk of the tree, and this is the cementite stringers. So when you view it under a microscope, it appears like the feathers of a bird. So it's called feathery bainite because it's formed in the upper transformation range 500, 550 to 400. It's called upper bainite. But in case of lower bainite, this cementite is precipitated inside in the form of fine platelets like this. So this is lower bainite. Lower bainite or acicular. Why acicular? Because of this pin type of a thing, right? Because this gets deposited inside also apart from this outside. So this is lower bainite. Lower bainite because it forms in the range, the lower transformation range of bainitic transformation 400 to 220. And students, this is that microstructure, martensite needle type in the ferrite matrix, supersaturated solid solution of carbon in alpha iron. So this is alpha iron ferrite, and you have these carbon particles in the form of cementites and other carbides deposited uniformly in the matrix of ferrite. So this structure is, this phase is called martensite. Mind it, perlite has got two phases in it. Bainite also has got two phases in it, but this is a single phase. Martensite is a single phase. Now I am trying to discuss with you that how did people start using the triple T diagram. See, people started saying that this triple T diagram is the temperature versus time curve. Cooling rates, when we cool the steel, the cooling rate at which the steel is being cooled are also temperature versus time. So we can superimpose different cooling curves on the triple T diagram, and then the triple T diagram would tell us that what transformation phases would be formed during the cooling of steel through austenite transformation. So somebody said, sir, we have taken a eutectoid steel containing 100% austenite. We are following very, very slow furnace cooling for it, as is shown by this sky blue line. Okay, so after this much of time, if we are following this cooling rate, after this much of time, transformation will start. Before that, we'll have 100% austenite. Okay, transformation will start, will continue to happen, and here transformation would end. What would become? The product would be coarse perlite. Okay, if we do faster cooling, this was furnace cooling, very, very slow cooling. If we do air cooling, okay, sir, this is air cooling. If we do air cooling, transformation will happen here, right? It would start at this time, it would end at this time. What would it form? It would form fine perlite. But then students, so this is how triple T diagram started being getting used. We found out the critical cooling rate also of the eutectoid steel. But then somebody said, see, what are you doing? You are assuming that you are cooling the steel through a given cooling rate, and this triple T diagram would tell you when austenite will begin to transform, when it will finish transforming, and into what it would transform. But was the triple T diagram made for these conditions? In triple T diagram, where did the transformation happen? In the second furnace. Under what conditions? Was it under continuous cooling conditions? No. The transformation was happening isothermally, that if you hold the steel at 680 degrees centigrade in the second furnace, after what period of time austenite will begin to transform, after what period of time it would have fully transformed. Now, how you studied the steel during construction of triple T diagram only under isothermal conditions. Yes, the temperature at which the steel was kept was a temperature lower than the lower critical temperature of the steel. So it was just a matter of time. Isothermally, if you kept your sample at that subcritical temperature, austenite was to transform. But you never transformed austenite under continuous cooling conditions. So how can you use that? So students, it was said that it is wrong to use triple T diagram to find out that during continuous cooling, how would the austenite present in the steel transform. But yes, if in any process the austenite transformation is happening as isothermally, for example, patenting, ostempering, martempering, isothermal annealing, then triple T diagram is okay. So this diagram, using it in this manner for continuous cooling conditions is not correct. And then the demand arose that we have to create another diagram, and that other diagram was called the continuous cooling transformation diagram. So we'll discuss it in the next session, students. I hope you have understood all the things. Thanks for watching.